All right, we are recording now and we'll cover HNSW to start with.
Yeah. Oh, let me share my screen. Next time onwards, I'll make PPTs. Okay.
Okay. Excalidraw.com.
And, uh, HNSW is Hierarchical Navigable Small World. Okay. I think there is something called, okay, how it started was, again, I forgot. Um, just give me 1 minute. Let me search that word. Okay. What is HNSW based on? This is where I'm very bad at actually. Uh, somebody, I don't remember now, I'm not able to find it out. Somebody came up with the concept that, okay, like, uh, in the world, there are some, how many, 7 or 8 or 10 billion people, right? So if um, you see, everybody is connected, everybody to or each other can be connected with at least 6 hop. That means that, like, I know you, you know somebody. Okay, by knowing, if, in 6 hops, you can reach anybody in the world.
Hmm.
If you see in the Facebook or LinkedIn, you see that, okay, first connection, second connection, right?
Yeah.
So in usually in the LinkedIn, by third connection, you are actually reaching almost everybody, I believe. Okay, the average jump you need to do, is around 3.5, I guess, in LinkedIn to reach somebody else. I mean, anybody else in the in that LinkedIn app. But in the world, I think it is 6. Okay. So based on that thinking, right? If you want to reach um, correct vector within the vector database, you don't need to actually check all the vectors, whether it is similar to this question vector or query vector. Okay, so you can navigate um, through this, like, search, HNSW search. You can think of like this. Okay, the query is a packet. I think this was the experiment done also in some time back by somebody. So what they did is that, they suppose you have an envelope to be delivered to somebody, some unknown guy. You don't know that guy. So what you do is that you know some 100 people, say, or you know some 6 people. Let's keep it simple. You know 6 people. Okay. Everybody else also knows 6 people. Okay. So you give to one of that 6 guy whom you think might know the be might knowing about that person, the, what do you say, the recipient of, who should be the recipient, or who should be the target, right? You think that, okay, person, let's say, let me put it in the drawing. Say we have the query, or we have to send this packet to some X person. Okay, so you know 6 persons. Okay, so you think that, okay, this guy might know about this person. So you send this envelope to this guy. Then this guy will be knowing about six people. So he what he will do is that he will think that who is the better person to pass this envelope to this the recipient. Okay, so he will select whomever he thinks is the best, and he will transfer that envelope to him. Like that, if you do, what will happen is that within six hops, you can reach anybody in the world. Okay, so that is the idea behind this. Uh, let's say, okay, let us think of uh, whatever the six hops I said, right?
Mm.
As like layers. Okay. So in this layer 0, you will have all the vectors. Okay. Complete all the vectors. Say you have injected some 30 million documents. So all maybe 30 million chunks. All these chunks are converted into the vector and stored in the database. So all this database, all these vectors, we will consider it as a in the considered to be present in the layer 0. Now, out of these vectors, you will choose randomly some specific number of vectors. Okay. There is a formula to this one. It is, I will I'll show that formula also. Okay, but let's consider that we are picking up some of this, not all, some of this. And this number of layers also is decided by the total number of the this one vectors present. Accordingly, the number of layers also will change. So I'm picking only few here. Okay. Now on the top layer, we'll pick even smaller number of uh, vectors. Okay. Just give me a second. I'll take my book. Okay. So how this is calculated is that there is a formula. Uh, let's say n is the total number of vectors, okay, total number of vectors present, and there is a decay factor. There's something called a decay factor, okay, and this will determine how much uh, vectors will come in the each layers. So decay factor is ML. I think ML is the representation of the decay factor. It is actually 1 by ln of M. Okay. So M is, what is this? M is maximum number of connections uh, each vector can have. Each vector can have. Okay. So now this vector can be connected. Let me take the different. This vector can be connected to this vector can be connected to this, this. In this case, you see that it's only connected to 2 or 3. 3 is the max. Okay, let's consider 3 is the max here. So these guys are also connected. All this 3 is the max. So m is equal to 3 here. Now you have a query. You have a query vector which actually falls here. Let's say here. Let me select somewhere here. Okay. If I come up, I think it will come somewhere here, right? And there is one more vector here, one more vector here. Let me put that also, okay? Okay, then here it will come somewhere here, right? Okay, now your query vector is here. Okay, so now it has to randomly pick first it will randomly pick any vector. Okay, let's say even this vector it can randomly pick. Okay, um, the algorithm will randomly pick a vector in the because it doesn't know which vector it is near to the query vector, so it will randomly pick one of the vector. Then between uh, then between this vector and the query vector, the distance will be calculated. Okay, and between this vector, there are two connections to this current vector, right? Between between those two vectors also, the distance will be calculated. The between these two and between these two. Okay, now there are three distances. Out of these three distances, which is the nearest one? Okay, this vector is the nearest one to the query vector, right? So we will shift our focus from the vector we picked at the starting to the next vector which is nearest to the query vector. Okay, hey, you got it this one right? Or am I very slow or boring or
Not like that. I have a question here that when you
yeah,
randomly choose a vector, right? You
mm,
choose only one vector, or you're choosing other vectors
one
also
vector.
randomly?
No, one vector. So you have the query. Okay. So you need to start from somewhere in the layer 0, right? And you don't know which vector is near to the query vector. So you randomly select any one vector.
Okay, like you pick the one on the leftmost.
Yeah, I picked the one on the left most.
Okay,
Okay. Now that vector has two connections.
okay.
Okay. Now to whom it will pass
Oh,
the ball to next?
whoever is
Okay.
closest from the query vector. Okay.
Whoever is closer to the query,
Hmm.
right?
Hmm.
So now we found out that this vector is closer to the query.
Hmm.
Okay. Now next we this once the focus is on this vector, now we need to calculate who else is near to the uh, who the vectors which are connected to this vector, out of them who is nearer to the query vector, that we need to again calculate.
Fine.
So we will calculate the distance between these two. That one we have already calculated actually. Then we will calculate the distance between sorry, these two and these two, right? Okay. Now out of these three, now this one seems to be the closest to the query vector. Okay. Now this has two more. So the focus will be shifted to this vector. Now this has two more vectors, right? Now we'll calculate the distance between these two and also these two. Okay,
Hmm.
correct, right? Now you see that out of all these three, this is near to the query vector. Okay. Now, now there is no more calculation because even though this has two more vectors as a neighbors, they are already the distance between them is already calculated, and they are more far than the current vector. So the nearest vector is here, this one. So now next what we will do is that we will directly jump back to the second plane,
Okay, Pawan,
and
one
we
question.
will,
Sorry to
yeah,
interrupt. So on the
yeah,
top
yeah,
plane, right?
yeah,
The what you did was you picked up any random vector and
yes,
then its immediate neighbors and found the
yes,
distance of all those like three vectors here in this case with their curry vector. And then you keep on
yes,
moving from vector to vector across all the vectors of the plane, across the plane,
yes,
going through all the vectors and finding
yes,
their distance from the query vector. And whoever has the least distance will go down to the plane as per that query vector, as
yeah,
per
yes,
that nearest vector. Okay, okay, okay.
as per that nearest, yeah. So
Same
once
process
we have,
repeats here also. Same process will repeat in the other
yeah,
planes also.
same process will repeat here also.
Hmm.
Okay. Same process will repeat here also. I think here the way I have shown it may not move much because this seems to be almost the nearest vector, right? Or we can even think that this is the nearest vector.
Hmm.
Okay. Or this is the nearest vector, whatever. So let's say we found that this is the nearest vector
Hmm.
and there is no other nearest vector. It will move back down here. Okay. And then again here also it does the same thing. So here my picture may not be very intuitive. But what happens is that here you just think that uh, here there are a lot of small, I mean, there are a lot of vectors very nearby. Okay. And the
Hmm.
concentration is more, means concentration overall concentration is more. Here the concentration is even more higher. Okay.
Hmm.
You understood, right? So when you come here, you will get a cluster concentrated space to search. Here you are searching on the very sparse space.
Hmm.
I hope I am able to make you understand. Think of it like here there are a lot of vectors actually in the down in the layer 0,
Hmm.
which we have not put in the layer 2.
Hmm.
Okay, we are not considering, but these vectors will be considered in the down layers
Hmm.
for the calculation.
Hmm.
Got it right?
Yes, yes.
Or let's even take a different this one. Let's make it like let's
Uh,
make it like yeah, we don't
so
have this way.
even if uh, even if e- I mean, do we have to search the distance between the query vector and all the other vectors in all the planes? Okay, then why don't we jump directly to the layer 0 and find it there directly, whichever is the nearest to
Ah,
that?
yeah, I'll tell you that.
Hey,
Let's say
Pinakini joined in. Hey, Pinakini.
hey Pinakini.
Hi, Vinay. Hi, Pawan. Sorry, I
Hey, hi.
saw the message late just now. I
That's
saw and
okay.
I joined.
That is okay. We are we
Discussing.
change the time. Okay,
Okay.
just to give an what we are discussing, okay.
Hmm.
So in the RAG, we discussed the RAG model. Maybe we can have
Okay.
a brush up of that one for you today. Then in the RAG model, there is indexing and retrieval, right? So
Hmm.
indexing means we convert the documents into chunks and chunks into the vectors, and those vectors we will put in ingest into the vector DB. That is the indexing pipeline.
Okay.
Okay. So in that, there are few algorithms which helps to index in such a way that retrieval is very fast. Even if you have billions of chunks or documents, you don't need to search all the vectors in the vector DB, and it helps to minimize the computation. Okay, by reducing the search area. So that in that one of the or the popular mm,
Algorithm.
algorithm is HNSW. Okay, that is what we are discussing now. It is hierarchical navigable small world.
Okay.
Okay, it's a graph-based uh, search actually. So yeah, okay. So we have the query vector. I'll just quickly go over from the starting, Vinal. Okay. So
Yeah.
we have the query vector. This is the vector. Okay, we in this HNSW we can have multiple layers. Okay, and the layer 0 is the layer which contains all the vectors, and layer 1 contains selected, it's actually randomly selected vectors, but it will have lesser number of vectors than the, I think Vinal joined twice.
Yeah, actually, I joined twice. That's fine. That's fine. You carry on.
Okay, so in the layer 0 will contain all the vectors. Layer 1 will have lesser number of vectors than layer 0, and next layer, layer 2, will have even lesser number of vectors than layer 1. Okay, then once a query comes, so this is the vector DB, say this is the vector DB, a query comes, query vector. We have a query
So,
vector.
one question. So these are logical layers, is it? Or like how are these
Yeah,
layers?
right, logical only.
Okay, okay.
Yeah,
But
so
Pinakini, how familiar are you with RAG? Like, do you know what RAG is and how it works?
Yeah, basically no, Vinal. Yeah.
Okay, cool then.
Basics I know.
Cool. Yeah, Pawan, sorry, Pawan.
yeah, so now we have selected a query vector here. Okay, this is our query vector. Okay, and it actually falls here in the plane. But if you see a vector, you will not know where exactly it falls. Now, in the layer 2, in the topmost layer, you have the minimum number of vectors. Now you need to find the nearest vector in the layer 2, which is nearest to the query vector. But first, what you will do is that the algorithm randomly selects some vector, okay, as an entry point. Then each vector is connected to the other vectors. What is the maximum number of vectors it can connect to? Means it can be connected is defined by the I mean letter M. Okay, so in our case, in this whole uh, this space, we have considered like each vector can connect to three other vectors. Okay, so in our case m equal to 3, so it is a maximum number. So here you see, let's say I'll put one more dot here, so it is 3, and others are having 2 connections. So now first we selected this vector. Now we will find the distance between, I'll call this vector as A. Find the distance between A and the query vector. Okay. Then we have to check which of, I mean, now we need to move towards the query vector, right? Now we are in the vector A, we need to move towards the query vector. So what we will do is that we will figure out what is its connected vectors. It has 3 connected vectors. Now we will check what is the distance between those vectors and the query vector. Okay. So now after calculating all four of these, now we have to check which has the lowest distance. Okay. So we can see that vector B is having the lowest distance to the query vector. Then we will move our focus to vector B. And we'll do the same thing again with the vector B's neighbors. Vector B has only two neighbors. Okay, and A and query vector's distance we have already calculated. Let's say this is C vector, and now we will calculate the C and the query vector's distance. Okay, and is it lesser than the B and Q? If it is lesser than B and Q and C is nearer to the query vector, we move the focus to the C vector. Hey, Vinal, this is fine, right? I hope I'm clear.
Good.
Okay. Now you can calculate again, say this is D vector in the same way, whether that is nearer than C vector. But this is obviously far than the vector C. So C is the nearest to the query. So in this plane, we have finished our calculations. Okay. So there might be other vectors also here. So which we don't use for the calculation because we have traveled in this path, right? We have traveled in this path. So there might be different other vectors also, which don't need to be calculated. So we have saved that part or that computation. Okay. And now
No,
once we
Pawan,
have found a,
sorry, this computation save
yeah,
part. How do you say the
yeah.
computation? Like you have to run through all the vectors in a plane and figure out its distance with the query vector, right? So
No. I
how
mean,
do you do?
no. See here, if you have this vector here, this vector here, or this vector here, and this vector here, you are not going to worry about that, right? See, already this vector we calculated. Okay, this vector is far. This distance is far, right? This distance, when we calculated the A vector, we found that next whom to pass the query, whom to pass the focus to. Okay, that we decided as B. This is the vector, B vector.
Hmm.
You got it right.
All right. So whatever neighbors are there, whichever neighbor is closest to the query vector will follow that neighbor's path. That's it. Okay.
We will follow that neighbor,
Hmm.
okay, which is the nearest to the next. I mean, in the analogy, what I said, right, in the envelope, and this one, you have six friends. You will pass to somebody whom you think might be knowing the recipient better. Then
Yeah.
you will pick the best one out of the six guys, six friends. So it's like that. So
Hmm.
you completely forget about other five people. Okay, you will only pass it to one of them. So from B we came to C, and anyways D is far, and there is no other
Neighbor.
connection to C.
Hmm.
Yeah, and we will D might have different neighbors. That doesn't matter because D is far than C, right? D is farther to Q than C, so we don't pass that control to D. So then once we have decided C is the most nearest, we will come to the C in the second plane. Okay.
Hmm.
Okay. So
And
in the second
how
plane,
many hops you cover? Sorry, how many hops you cover? Like how many? Like there will be like millions of vectors maybe in a huge vector database, right? So
uh-huh.
even in plane two. So how many vectors we have to jump? Max we can jump to reach the closest one to Q.
How many vectors? That I don't know, man. Okay, let me do one thing. I'll quickly check. Okay. Don't know.
Like that's okay. I'll note it down. We can take it up at the end
we
maybe.
can take that also.
Yeah.
Jump within a plane, right?
Yeah. How many jumps it will do to seal on the vector that is the closest to Q and go down with that vector in the next plane. So how many hops you jump to reach at that
No,
vector?
there is no fixed number of vectors you can jump within a plane or layer. Okay, there is nothing like that. So why it is not there probably
Hmm.
is because if you see one example, I think you will come to know.
Okay.
Okay,
All right. All right.
maybe we can take one example. It's a bit complicated. Even I don't know that many details, but I'll try to explain that, or we can ask the ChatGPT and also see. Okay.
All right. And
Yeah,
as
just hold that question. Okay.
okay. All right. And as that m, the number of connections each vector has in a particular
Yeah.
plane, as the m
Yeah.
increases, obviously the competition will increase for us. Okay.
Yes. As M increases, computations also increases. Yes.
All right.
That yeah, that is also one defining factor, and also M is used to M also will come into picture how much vectors you can keep in a plane. Okay.
Hmm.
So decay factor is based on M, right? So decay factor will decide how much vectors you can keep in different planes.
Okay.
Okay, so once we figured out what is the nearest vector in the plane, top plane,
Hmm.
now in the second plane, which will have more vectors than the query vector.
Hmm.
Okay, so you think that we have this many vectors. Okay, it is more than. Uh, Let me remove few things to make it bit clear.
As
Oh,
we keep
sorry.
going down, the density of vectors will keep increasing. Yeah. Okay.
Yeah, keep increasing. Yes.
Hmm.
So what I'll do is, yeah, I think
Oh,
this
one more
is
question.
fine.
Sorry. Will M change as per the planes? Like M is different. M is less in the upper planes, and M becomes more in the
No,
as we
no,
go
no, no,
down.
no. It's the
No.
same.
Okay.
It's the same.
Okay. Okay.
So now you have figured out this C is the final vector in the layer 2. So we come to the layer 1. So this is C. Let's say this is C. It has again few connections here, all those things. And we will do the same navigation and computation, whatever we did in the layer 2. And we'll figure out that this is the final vector. Okay. I'll mark it with the red, maybe. Okay, this
Hmm.
is the final vector in the layer 1. So now you see your distance, your the vector you selected in the layer 2 was C. C was comparatively far to Q in the layer 2, and then let's say this is the E vector. Okay, then the E vector which is in the layer 1. So now you are moving towards the query vector, right? So let's say all these vectors, if you had directly come into the layer 1, what would have happened? There would have been lot of vectors. You would have to navigate lot of vectors, right? You would have been end up with a lot of hopes. You would not have reached this space itself. I mean, you would not have reached the queue. You would have
Hmm.
I mean, you could have reached it, but with a lot of computations, right? Because it is a dense space,
Hmm.
isn't it? That is why you first search in a sparse space. You keep like